This video will be about projectiles that are launched at an angle. So objects launch at some angle relative to the horizontal. So the most basic type of problem we can have in this topic is an object that's launched at some angle and lands on the same level that it's launched. Now, the most important thing to remember with these problems is that this velocity here needs to be broken up into components. Specifically, an x component and a y component. So if I have a velocity v at an angle theta, the x component, vx, is the horizontal side of the triangle, and the y component, Vy, is the vertical side of the triangle. Because the Vx side is adjacent to the angle, that means I can find Vx by doing V, the initial launch velocity, times the cosine of theta. Since Vy is the opposite side of the angle, I can find Vy by doing V sine of theta. So that's my first step, and honestly, once we get past this first step, projectiles are exactly the type of problem we already know how to do. So let's talk about the x direction to begin with. So we know that in the x direction, this object is moving with a speed of v cosine of theta. Okay. We also know in the x direction that this object is not accelerating because there are no forces acting horizontally on the object. So as the object flies through the air at various points, no matter where the object is, it will always have the same x direction velocity it started with. So if this arrow here represents Vx, all of these other points have to have exactly the same arrow length. And I tried to draw those approximately equal, but they all have x component values of Vx. So that Vx never changes, which means in the x direction we are undergoing constant velocity. Now, really the only equation we can use for constant velocity is our position versus time equation, but because acceleration is 0, this whole third part goes away. So in the x direction, we can use x equals v0 t, and we know how to do a constant velocity problem already. So the x direction is the easier of our two. The y direction is slightly more complicated, but still not really that difficult. So in the y direction, we have initial y velocity of v sine theta, or that initial y component. The acceleration in the y direction is always going to be negative 9.8 meters a second squared, because as this object flies through the air, only the force of gravity is acting on it, so our acceleration is equal to the acceleration due to gravity. We also need to keep in mind that the velocity in the y direction at the peak is 0. That's because objects have to stop at the top. In the y direction. We're still moving in the x direction. So in the y direction, we are exactly the same, or we have the same motion as an object thrown upward. So this object slows down on the way up and speeds up on the way down. So if I was to draw in some velocity vectors, right, if my initial velocity in the y direction looks like that, I have to get shorter and shorter until I have a Vy of 0 at the peak. And then on the way back down, my arrows need to get longer and longer. Let me make this middle one a little bit shorter. Okay. So I slow down on the way up, speed up on the way down. Now the acceleration throughout, a lot of students make the mistake of thinking that the acceleration is 0 at the peak as well. That's not true. The acceleration of this object, no matter where it is, is always 9.8 meters a second squared. So just keep that in mind. And even though that acceleration is in the y direction, there's no other acceleration, so that also represents our total acceleration. So in the y directions, the equations we can use are the position versus time equation. Instead of x's, I'm going to use y, so I remember that this is the y direction. I can use the velocity versus time equation, and I can use the timeless equation for all of the values in the y direction. Okay. Now, big thing to remember is that the only variable that is the same between these two is time. Okay. So our time is the same between the x and y direction, but that's it. Velocities can't cross over, accelerations can't cross over, only time. Okay. So if you remember from horizontal projectiles, that time is dependent on the y component. So if we change anything about the y component, then we're going to change the time. So if we increase or decrease this initial y velocity, we're going to change the time we're in the air. So the way we change that y component is by changing the angle or even changing the initial velocity. So let's do an example. So let's say I have an object launched at 20 meters a second at an angle of 30 degrees. Okay. So in the x direction, my initial velocity is v cosine theta. So 20 meters a second times the cosine of 30 degrees, making sure that calculators are in degrees. We get a value of 17.3 meters a second. And in the y component, we know Vy is v sine theta, or 20 times the sine of 30, which is going to give me 10 meters a second. Okay. So this problem, at the same time, is an object that's thrown upwards with a speed of 20 meters a second, and an object rolling across the surface at a speed of 17.3 meters a second. So most common things we might be asked to find for a problem like this are, first and foremost, probably the maximum height. So maximum height is a y direction thing, specifically a change in y. Okay, remember, we know the acceleration in the y direction is negative 9.8 meters a second squared. We know that velocity at the peak, or that maximum height, is 0, which can occasionally be a v final in our equation. So an equation that has these four, and only these four variables in it, is going to be v squared equals v0 squared plus 2a change in y. So I'm using v peak as a v0 since my maximum height occurs at the peak. So v0 squared equals 10 meters a second squared plus 2 times negative 9.8 times delta y. So that ends up giving me a change in height of 5.10 meters. That's a change in height. Wow. Right. So that's my maximum height. So max height. I then might be asked to find the time of flight. Right? So time. Again, time is y direction dependent, so I'm most often going to use the y direction to find it. Okay. Since we're doing total time of flight, I can't use this v peak of 0. So I have an initial velocity, a displacement, and an acceleration, and I need to find time. So if I'm using y equals y0 plus v0 t plus 1/2 a t squared. Well, if I'm just about to land to find my total time, my final position is 0. My initial position is on the ground, so that's also 0. Then I have 10 meters a second times time plus 1/2 negative 9.8 meters a second squared times time squared. So this gives me 0 equals 10t minus 4.9 t squared. So I can move this 4.9 t squared. Okay. A time can cancel, or a t variable can cancel, so I'm left with 4.9. T is 10. Divide both sides by 4.9. And I get my time is about 2.04 seconds. And again, that's total time. Okay. So now let's say the question asked me to find my range. So range is an x direction distance. Okay. So that's my change in x. Again, that change in x is often considered the range. Only equation I can use in the x direction is my constant velocity equation. I'm looking for my final position. We can assume my initial position is 0. Velocity in the x direction is 17.3 meters a second. And remember, time is our crossover variable, so I can write 2.04 seconds here. So I can do 17.3 times 2.04, and that gives me a final x position, or a range, of 35.3 meters. So we can use all of these equations to find the x position at any given time, y position at any given time, y velocity at any given time, y velocity at any given height. So just remember to draw that out, or write out your two lists. Where things can get slightly more complicated is if we launch something at an angle from a certain height. So let's say we take that same 20 meters a second, but launch it from a height of 15 meters. The only thing that's really going to change in our treatment of this problem is not anything about the initial velocities. Okay? Those are still v cosine and v sine, so this is still 17.3, and vy is still v sine, so this is still 10 meters a second. Okay? Now, because we're being launched from a cliff, we're going to have a slightly longer time. We are going to have a height that is an additional 15 meters from the ground, and we're going to have a range that's a little bit longer because we've increased the time we're in the air. So our maximum height, if we can find the maximum height to the peak, or the height to the peak, so in this case 5.01, that means our maximum height is 5.01 meters from the top of the cliff, or a total height of 20.01 meters from the ground. So not really much different in our maximum height. Okay. To find the time, it does get slightly more complicated. Okay, so again, we know our acceleration is negative 9.8 meters a second squared. We know our total change in y, if we start up here and to end down at the ground, is negative 15 meters, because we start at an initial height of 15 meters and we end at a height of 0 because we're on the ground. And if I need to find the time, then I need to use the position versus time equation. Okay. So my final position is 0. This is 15 meters plus 10 meters a second times time plus 1/2, negative 9.8 meters a second squared times time squared. Okay. Now, unfortunately, the only way to solve this problem is with the quadratic equation. So the idea that t equals negative b plus or minus the square root b squared minus 4ac all over 2a. And you're probably thinking, why the heck would anybody ever have us do that on a test? Realistically, you would not have to do this on a test, but it's important to know how to do it. So we would do t equals negative 10 plus or minus 10 squared minus 4 times a is 1/2 times negative 9.8, and c is 15, all over 2 times negative 1/2 times 9.8. Okay. Now this is going to give us two answers for time. One is going to be positive, one is going to be negative. Obviously we can't have negative time, so we would just take the positive one. Okay. And that is actually not about it. One thing I do want to keep in mind is that at any point in time, you might be asked to find the resultant velocity or just the velocity without any x or y component just before we hit the ground or at any point in time. So at any point in time, our velocity is made up of some y component, Vy, and an x component, Vx. Remember, if I want to find a resultant velocity or a total velocity, these two vectors need to be head to tail. So I should draw them like that. My resultant velocity would look like this. And that would be the angle with horizontal or the angle with ground. So if I wanted to find V, I would do Pythagorean theorem. And if I wanted to find theta, I could use tangent of theta, where tangent of theta is Vy over Vx. There are also ways to find that speed using energy, which can be especially useful in an example where you are launched off the top of a cliff. Because remember, at this point here, when you're launched off the top of a cliff, you're going to have potential and kinetic energy. At this maximum height, you're going to have potential and kinetic energy, but that kinetic energy is from the x direction velocity only. And then when we land down here on the ground, we're only going to have kinetic energy because our potential energy is going to be 0. So we can also solve these problems using energy if we need to, and we should keep that energy part in mind. Okay? And this KE is based off of the 20 meters a second in the beginning. Other things to keep in mind for this type of stuff is that you might be asked to do graphs. So we might be asked to graph position versus time. Okay, we might be asked to graph the y component of the velocity and the x component of the velocity. So the x component of the velocity, since it is constant, is just going to be a nice horizontal straight line at the value of the x component. The y component, on the other hand, is going to start at some value, whatever that value is. It is going to decrease with respect to time until we reach the peak, where the velocity in the y direction momentarily becomes 0. And then we are going to increase in the negative direction. Remember, this is when we are moving downward. So we're going to be speeding up, and this is when we are moving upward. Okay. We might also be asked to look at position versus time for the two directions. So in the x direction, our position versus time is going to increase linearly as time goes on to correspond with that constant velocity. Okay. Our y direction, on the other hand, is going to increase as time goes on until we get to our maximum height, and then decrease until we get back to 0. Okay? If we're launched from some initial height, so this would be if our initial height was 0. If we're launched from some initial height, then our graph is going to look something like that, okay, where we have an initial y direction value. Okay. And those parabolic graphs match with an object that slows down on the way up and speeds up on the way down. Its concavity, or the opening of the parabola, is downward in both cases, which represents negative acceleration. The last thing I want to talk about is some important angle information. Okay. So 45 degrees is going to give us our maximum range, which is that maximum change in x. Okay. Increasing theta is going to lead to an increase in time and an increase in our maximum height. Okay. So we end up with a maximum height and maximum time at 90 degrees. And one really cool thing is that complementary angles So that could be something like nope, not 90. Oops. Two angles that add to 90, 70 and 20, 60 and 30. Okay, they have the same range. Okay. So 70 degrees is going to be in the air longer, which we might think might lead to longer range, but as theta increases, the cosine component decreases, so the Vx decreases. Okay? So the decrease in Vx is made up for by the longer time in 70 degrees. So it ends up having the same range as 20, which is in the air less, but this Vx value is larger. Same thing with 60 and 30. And the derivation of that comes from some double angle formulas for complementary angles. If you want to know how that happens, feel free to look it up. But for now, just remember that they have the same range. Okay. And that is pretty much it for projectiles at an angle. The end.